by putting this into the context of our new favorite plot. So this is the phase diagram of cosmic structure. At the large scales, we have, let's see, here. We have the density fluctuation phase at high redshift or large scales. Here we have the X phase. And then we have the halo phase. So if we want to, so I want to extend this picture down to the free streaming scale. So we don't know what the free streaming scale is, but we expect that there is one. So I claim that at the free streaming scale, there's another phase, the prompt cusp phase. So this story starts with the cosmological initial conditions, the density perturbation phase. So we have a random density field expanding over time, getting gravitationally amplified over time. But we expect that this is, if we look at small enough scales, this density field is smooth, typically due to thermal motion of the dark matter. And in a smooth density field, there are well-defined local maxima. And those are going to be the first places to gravitationally collapse. So here is what that looks like. So we have a local maximum in the density field getting kind of smoothly amplified until at some point it essentially collapses into a compact structure all at once. And here is what that structure looks like. So I'm showing the density profile. This is density as a function of radius, going from early times in purple to later times in red. And so kind of the main thing to notice here is that this is a straight line. So it's a pure power law. Actually, here's the same plot, but now I've multiplied the density by radius to the 3/2 power, and it's a horizontal line. So that means we have an r to the minus 3/2 density cusp. And actually, the most interesting feature of this picture to me is that this cusp is set immediately at the moment of collapse of the density peak. So this is a prompt cusp. By the way, if you're looking closely, you'll see some of these spurious fragments that Frank talked about. I just want to point out that this result is robust. It's been confirmed in phase-based simulations. Okay, so the fact that the cusp is set immediately at the collapse of the peak is really important because it means that the properties of the cusp can be only sensitive to the immediate neighborhood of the initial density peak. So here's an example. This is the density contrast as a function of co-moving radius. And here we have a local maximum at the center. And so we can parameterize this by the height of the peak, and so like the amplitude of the maximum amplitude of the density contrast, and the characteristic size of the peak, which is set by its curvature. We can combine the height with the tidal field at the peak to get a collapse time. This is just standard ellipsoidal collapse. And now when we have the collapse time and the co-moving size, there is only one way to put those together to get the cusp structure. So its density has to be related to the density of the universe at the collapse time, and its size has to be related to the physical size of the peak at the collapse time. And so there are some numerical coefficients here. You can tune those to match simulations, but the important thing is that they don't depend on cosmology. They're just set by gravitational physics. So this prediction works quite well for all of the collapsing peaks that I've tested. So I'm showing 4 examples here. I've tested thousands. But okay, so here is, each of these is a different simulation of a different peak. It's actually a cosmological simulation, but I'm like zoomed in on the peak. So density profile, density times radius to the 3/2 power as a function of radius, going again from purple at early times to red at later times, and the prediction is in black. So in all of these cases, the prediction matches the simulation quite well. Okay, so I've established the connection between a prompt cusp and the density peak that formed it. But what is the distribution of peaks in the first place? Well, that actually follows directly from the linear matter power spectrum in a way that has been well understood since, well, a long time ago. So here is just kind of an illustration of what that looks like. So we can take some random dark matter model. We want to look at the linear matter power spectrum. Here I'm showing actually the dimensionless form. So this is essentially telling you the squared amplitudes of density contrasts as a function of the wave number. So here's what it would look like with no free streaming, but because of free streaming, you get you smooth the density field, so you're going to kill all the small scale density variations. The prompt cusps are going to form at that smoothing scale. And so you just run that peaks calculation. You get a distribution of peaks, so in co-moving size and collapse time. And then you can just use this association with the prompt cusps to say what's the distribution of cusps in mass and radius. So I don't want to dwell on those numbers too much, just kind of an illustration of what that calculation gives you. Because I want to emphasize that this can be done easily for any power spectrum. So this relates to, of course, the properties of the dark matter. We could have warm dark matter with a much larger smoothing scale, or we could even consider much colder dark matter. And this also connects to the physics of the early universe, because you could change the primordial power spectrum, for example, due to inflation. You could think of other early universe physics, like a period of early matter domination. Actually, Himanish Ganju worked out some observational implications of prompt cusps in early matter domination scenarios. So there's one more feature of prompt cusps, but actually not just prompt cusps. Any cusp that I wanted to point out, and that is, so I'm saying that, well, the initial density field is smoothed by thermal motion of the dark matter, but that thermal motion should also affect the internal structure, and it affects it in this way. So here is so it leads to finite density cores at the center of any cusp. And here's a picture of what that looks like. So this is a density profile, density as a function of radius. This is from a group that simulated this. So what they did is they looked at a halo in a simulation, and they increased the initial velocity dispersion in the simulation. And as they do that, the maximum density goes down. So I should point out there's no prompt cusp here because they deliberately increased the velocity dispersion without correspondingly increasing the smoothing in the initial conditions. Okay, so we can calculate this analytically, and the idea is to use conservation of phase space density. That's Lubiel's theorem. So you can evaluate the maximum phase space density in the early universe. That's essentially the spatial density of the dark matter divided by the volume that it occupies in velocity space. And then you say that, well, this maximum phase space density cannot be exceeded inside any later structure. And that imposes this equation for the core radius and core density. But yes, so you run this calculation for just some range of dark matter models. So I find that typically the ratio between the cusp radius and the core radius, so that would be the kind of the range that this r to the minus 3/2 density cusp covers, is typically around 500, but that depends on the dark matter model. Okay, so I talked about how prompt cusps arise from, like how they form, how they arise from peaks in the density field. But you might wonder, well, do they actually survive? So, like, are they relevant? Well, so this is the picture I showed you before, but what happens to this object over a much longer time period? So this is what happens. Here's the same kind of plot. So this is the density profile, density times radius to the 3 power as a function of radius, going from earlier times in purple to later times in red. And so what's happening here is, okay, so you have this initial prompt cusp, and then over time, we build up material at intermediate and large radii. And actually, that buildup leads to a standard halo density profile. This is an asto profile. But at the center, we still have the prompt cusp. So the result here, so here's another plot. This is without the rescaling, just so this looks more familiar. The result is we have a standard dark matter halo with a prompt cusp at the center. So actually, this is not this kind of result should not be surprising. It's kind of a standard thing that you see in halo growth, that when a halo accretes material, the new material has too much energy and angular momentum to sink to the center of the system, so it ends up mostly just contributing to the outside, and that's why we just see the buildup of density here. Okay, so prompt cusps survive halo growth, but do they survive halo clustering? So another way to put this is, well, so I said that I can associate each initial peak with a prompt cusp, but how valid is it really to say that every peak can be associated with a cusp? So here's an estimate from a simulation. So this is essentially the number of prompt cusps as a function of time. This solid curve is what you get if you just look at the number of peaks that are predicted to collapse. The dotted one is what you get if you look at the number of peaks that actually do collapse, and the difference here is because some peaks are going to fall into already existing halos before they can themselves collapse. And then the dashed line is what actually survives. But hold on, we know that surviving, so we know that simulated subhalos are artificially fragile. There's been a lot of work showing that cuspy subhalos cannot be destroyed by tidal forces. So we should actually, we should correct for that. And once we correct for that, we get kind of this band of estimates. The correction is to say that a subhalo can only be destroyed if it sinks into its host's center. So the outcome of this is to say that about half of collapsed peaks can be associated with prompt cusps. This kind of squiggle here is not too satisfying. I'm currently working on improving that. So, okay, another really interesting question. Do prompt cusps survive locally? So it turns out that yes, actually a significant fraction of the prompt cusps can survive at our own position within the galaxy. And so here's an estimate for some random model. So I'm showing the distribution of prompt cusps. This is actually distribution in annihilation luminosity, but should be similar for other properties. So dotted line here is the distribution if you don't account for subhalo evolution. Dashed line is if you account for tidal forces. So what happens is you get kind of a mild effect on all of the prompt cusps. And then the solid line is if you account for encounters with stars. And so what's happening here is that about 2/3 of the cusps are essentially destroyed, but around 1/3 of them are pretty much unaffected. Okay, this is all based on the excellent modeling of stellar forces, tidal forces and stellar encounters by Jens Stucker. Okay, so I've looked at some implications of prompt cusps. So for WIMP dark matter, the annihilation rate overall throughout the universe is boosted by a factor of about 10 compared to previous estimates. So here's a picture of what is essentially the annihilation rate per mass of dark matter as a function of redshift. So we can look at the prompt cusp prediction and compare it to previous halo and subhalo models. Now, okay, we can go to larger smoothing scales, think about warm dark matter. The prompt cusps in warm dark matter models could affect galactic kinematics. So I'm showing an example here. So these are, observationally inferred density profiles of some classical dwarfs. And then I'm overplotting where we would kind of expect the prompt cusp to be in these warm dark matter models. I should note that classic, you can do better with ultrafaints, but you don't get plots that look as good. Okay, but I want to emphasize again that prompt cusps arise much more broadly, and you can predict them straightforwardly. And another point is that prompt cusp properties depend sensitively on the matter power spectrum. So you can look at how narrow these distributions, the cusp distributions are. They're about a decade in mass, a decade in radius. I mean, a decade isn't that narrow, but if you compare it to halos, right? Halos forming all masses. So this means that detection of a prompt cusp, like even just one prompt cusp, would tell us something really precise about the nature of dark matter or the physics of the early universe. Also, kind of a small point, a lot of us are kind of hoping we're over here and we're going to start seeing effects of the dark matter at galactic scales. Or maybe we're over here and we're going to find dark matter non-gravitationally. But, well, what if we're in a nightmare scenario? So dark matter is really heavy, doesn't have a non-gravitational interaction. It could be that the prompt cusps are the only experimentally accessible signature of the dark matter. The idea is, well, okay, maybe the dark matter is heavy enough that the prompt cusps are this big. Well, remember, they do survive locally, so they would be passing through the solar system, they'd be passing through the Earth. We could try to gravitationally detect them. Okay, so my summary. Prompt are the minus 1.5 density cusps, form from the collapse of smooth peaks in the initial density field. They persist through halo growth and clustering. They even survive at our own position within the galaxy. And their properties depend sensitively on the initial mass and velocity distributions of the dark matter, and thus on dark matter properties and the early universe. So yes, I've drawn this phase diagram again, the modified phase diagram, and I claim that prompt cusps can be mostly predicted with linear theory. What I mean is that, so you can predict their formation really straightforwardly, but there's some complications because of interactions with the halo phase. And I want to end on maybe a bit of a provocative claim. So we heard a little bit about kind of spurious halos in simulations, and that might lead you to wonder, well, how do you even define what a halo is? So I've been telling you about what prompt cusps are, but now I want to turn around and tell you what a halo is. A halo is the atmosphere of a prompt cusp. Thank you.